All right, so let's talk about two-dimensional interference math problems. So let's say I have source 1 and I have source 2. And let's say I know that the frequency of source 1 is equal to the frequency of source 2, and we'll make that, 50 hertz. Great. And then let's say that we know the speed of the wave in this medium, right? Let's say the speed of the wave in this medium is 25 meters per second. That means the wavelength, whoops, I'm out of bounds there. The wavelength here would then be V over F, or 25 meters per second over 50 hertz, and the wavelength then is 0.5 meters. So each of these is putting out a wave whose wavelength is 0.5 meters. So let's say that D here, the distance between the sources, is, 3 meters. So D equals 3 meters. So the question then becomes, if I pick a point somewhere here, let's say I pick a point here, and point there, let's call this distance X, and saying, what is X such that point A, we'll call this point A, is on the, let's pick something, maybe the third order antinodal line. Okay. Oh dear. Okay, so here we go. How do I figure this out? Well, it's actually not too bad, because a third order antinodal line, what do I know about the third order antinodal line? Well, I know the path difference to the third order antinodal line would be 3 times the wavelength. Okay? So in this case, that means that our path difference is 3 times 0.5 meters, or that's 1.5 meters. All right, so that's going to be super helpful. So now let's talk about path difference. Well, from source 1 to point A is X. Well, how far is source 2 to point A? Well, just got to do a little bit of geometry here. I made it nice and easy by making this a right triangle. So I think we can see that this is just going to be the hypotenuse. So that's X squared plus 3 meters quantity squared, and there it goes. So we're saying that the path difference here has to be equal to absolute value of L1 minus L2. All right. So here we go. So 1.5 meters has to be, and it's absolute value. So I'm just going to arrange these so I get a positive value here. That just makes my life a lot easier. And so that's going to be the square root of x squared plus 9, because I've already done the plug-in with units the first time, minus x. And now what I have to do is I have to solve for x. Well, that's annoying. So how am I going to do that? Oh, I got it. I have to square both sides, but let's move some stuff around to make that squaring a little bit easier. If I do 1.5 plus x, add x to both sides, I get the square root of x squared plus 9. This is a lot nicer to square, because then I can get rid of all of my radicals. So this is x squared plus 9 on this side, and this is 1 plus 5 plus x, or 1.5 plus x quantity squared. So I'm going to expand that side now. 1.5 squared is 2.25 plus 2 times 1.5 times x, so 3x plus x squared is equal to x squared plus 9. All right, you can see if I subtract x squared from both sides, that goes away. So I have 3x is equal to 9 minus 2.25. So 3x is equal to 6.75, and divide across there, so that's 2.25 meters. So if x is 2.25 meters, point A is on the third antinodal line. So there you go, nice and simple. So given a condition, we can create a math equation and go from there. let's do it sort of the opposite way now. Rather than given a condition, we're just asked something about what's true about a point. Now, I'm going to warn you, I'm absolutely just about to make up numbers, so I don't know how this is going to work. Let's say we know this point in space A, and let's just say from a geometric standpoint, I'm told that this is, I don't know, 5 meters, and then this is just something smaller than that, say 4 meters, okay? And I'm asked, well, what's happening at point A? So let's say that source 1 is equal to source 2 again, because we're going to do these for equal frequencies, and we'll just switch it up here. Let's say that these are 100 hertz, and let's say that the speed is something different here. We'll make that 40 meters per second. Okay, so then the wavelength is V over F, 40 meters per second over 100 hertz, and so that's 0.4 meters. All right, so now when we look at this, path difference is equal to L1 minus L2, absolute value, and we can calculate that. Oh, okay, well, I'm kind of given a nice easy thing here, 5 meters minus 4 meters, which is 1 meter. So now the question is, the path difference is 1 meter, but the wavelength here is equal to 0.4 meters. So we know that this is supposed to be equal to n times lambda. So if I solve for n now, 4 divided by 0.4 is 2.5. So what must be true then? Oh my God, n is 2.5. That is a half integer multiple of wavelengths. Therefore, this must be a destructive interference. And very specifically, it's 5 halves. And we know that 5 halves, that's on the N3 line. So point A must be on the N equals 3 nodal line. And so that's the type of problem that you get with two-dimensional interference from a math perspective.